You're looking at your phone screen. Soft light. The sound turned low. A thin device no bigger than half your hand, weighing not even 200 grams, yet inside it lies a treasure chest which, if broken apart into individual elements, reveals a quiet truth. The entire modern world rests on particles so small no human eye could ever see them. Those silent elements carry an unassuming, almost rustic name: rare earths. Try touching the back of your phone. Just beneath the metal or glass shell is a neodymium magnet, one of the strongest magnets humans have ever created. It's the reason your phone's tiny speaker can produce clear sound inside a body so thin it seems impossible to fit anything inside. It's the reason your camera can stabilize itself even when your hand trembles slightly as you try to capture a moment of your life. As your fingers glide across the screen, those flickering dots of blue, red, and violet light, all of them bear the fingerprints of europium, terbium, yttrium, elements whose names feel distant, unfamiliar, yet they accompany you each day, from the moment you wake until the last minutes before sleep. Rare earths are also inside your headphones, your laptop, the electric car gliding past you on the road, the offshore wind turbines spinning in the distance, the navigation system guiding you home, the stealth aircraft above the clouds, and the cold MRI machine in a hospital where doctors diagnose some of the most important truths of a human life. Even the soft LED light filling your room right now exists only because a few rare earth elements can amplify and transform light in ways nothing else can. Almost everything that makes the world run lighter, faster, and smarter rests quietly on them. Yet these elements remain unassuming. No one proudly announces how many milligrams of terbium their phone contains. No one calls a neodymium magnet the heart of the 21st century. For decades, rare earths have been like nerves running beneath the skin of the world, invisible, unnoticed, but sever one strand and the entire system goes numb. Perhaps because they feel familiar yet invisible, when we look at reality, a reality of billions of devices exchanging information, millions of vehicles moving without pause, hundreds of satellites circling the Earth, we forget that none of this modern life appeared by magic. It is the outcome of journeys spanning billions of years, beginning far beyond the reach of any spacecraft. As you read these lines, imagine the night sky. No cities, no lights, only darkness in the Milky Way stretched above like a silver river. Somewhere along that river, billions of years ago, before our sun even existed, supernova explosions tore apart the cores of dying stars. The force of those detonations created pressures and temperatures high enough to forge heavy elements that the ordinary universe could never produce on its own. The rare earth elements you're touching through your phone today all come from those explosions, from shattered stars, from the ashes of the cosmos. Then, as massive clouds of gas swirled, those particles drifted, gathered, and folded into the spinning nebula that would collapse into our solar system. Earth formed from that stellar dust. Rare earth elements sank into the crust, mixed with other minerals, buried, compressed, and locked inside crystal structures so complex that humans needed more than 2 centuries just to separate one element from another. Before joining modern technology, rare earths were grains of cosmic dust lying motionless beneath the ground for hundreds of millions of years, untouched, unnamed, unknown, a journey so long that humanity itself appears only in the final few seconds of this billion-year film. And this is the true beginning of the story we're about to step into together. The story of the quiet elements that shape every modern civilization. Elements, once nothing more than remnants of dead stars, are now embedded in every critical technology of our species. Elements that travel from deep in the earth, into human hands, into laboratories, into warfare, into devices capable of saving or ending lives. Rare earths are not merely a mining concept. They are the bridge between an ancient universe and modern life. They are proof that everything operating around us carries a history far longer than our imaginations allow. They remind us that every convenience, soft light, gentle sound, crisp images, depends on elements that once drifted alone through the cold emptiness of space. And the question that remains, opening the door to the next part, is this. If rare earths are this important, then what exactly are they? Why are they called rare? And why does the modern world depend on them so deeply? When we begin asking what these quiet elements truly are, we're forced to step away from the soft LED light of our room and descend deeper into their real world. That world looks nothing like the sleek devices they help sustain. It is a world of rock, dust, sediment, of Earth's crust formed in prehistoric ages. To understand rare earths, we must begin where they live, in unremarkable stones lying silently beneath our feet. In scientific language, rare earths are the collective name for 17 chemical elements, 15 from the lanthanide series, plus 2 outsiders, whose chemical behavior resembles the lanthanides so closely that they are adopted into the family, yttrium and scandium. Their names feel as if they emerged from some ancient cosmic glossary: neodymium, terbium, dysprosium, europium, holmium, erbium, lutetium, flickering like syllables of a language no one has ever spoken outside a laboratory. But their names are not the strangest thing about them. The paradox lies elsewhere. Rare earths are not actually rare. In fact, some rare earth elements are more abundant than silver or platinum. They are scattered everywhere, from the Sahara Desert to the Himalayas, from the Amazon rainforest to the ground beneath your feet. So why call them rare? The answer lies in the way they exist. They never stand alone. Rare earths are like grains of pure sand mixed into an enormous beach, present everywhere, but never concentrated enough, never easy to extract from the parent rock. Unlike gold, silver, or copper, which can appear in dazzling veins, rare earths occur only as traces embedded within other minerals, tightly bound within complex crystal structures invisible to the naked eye. They are like whispered stories buried beneath the soil, audible only if you listen long enough. These elements possess unusual bonding energies, making the process of separating them one of the most painstaking tasks in metallurgy. You cannot split open a rock and hope rare earths will spill out as shimmering grains. You must crush it into powder, soak it in chemicals, filter it through acids, heat it again at high temperatures, then refine it once more. And if you do one step out of order, you lose everything. It's no coincidence that humanity spent more than a century isolating all 17 members of this group. This leads us to another paradox. Rare earths are not only scarce in nature, but they are also scarce in human understanding. They appear in forms so similar that early chemists struggled to tell them apart, even with chemical techniques. A single sample might contain 4, 5, or sometimes 8 rare earth elements, as if they prefer one another's company, refusing every attempt to be separated. And this very quality is what makes rare earth strategically irreplaceable. Each element has its own role, a unique capability that no other element in the periodic table can replicate perfectly. Neodymium and praseodymium form the strongest magnets for electric vehicle motors. Europium gives the perfect red in LED displays. Terbium stabilizes the green. Dysprosium withstands high temperatures in wind turbine magnets. Erbium amplifies internet signals inside the fiber optic cables connecting continents. Holmium produces unusually strong magnetic fields used in medical technology. Yttrium strengthens ceramics, enabling jet engines to endure extreme heat. Every tiny fragment, every atomic trace, holds a piece of the power driving the modern world. But there's another characteristic that makes rare earths so peculiar. They are notoriously difficult to refine. No matter how much ore you extract, Without the technology to separate, purify, and transform it, the material is no different from ordinary dirt. Advantage does not belong to the land with large reserves, but to the place capable of converting them into usable form. And this is what laid the foundation for later geopolitical shifts. Whoever masters rare earth separation technology holds the advantage. Whoever controls the refining chain controls the future. Looking back, rare earths resemble an ancient code written into stone. They lay there, nameless, for millions of years, waiting for humanity to become knowledgeable enough and ambitious enough to decipher their language. Since the moment early chemists noticed their strangely indistinguishable presence, humanity has been on a quest stretching more than 2 centuries. And this journey did not begin with modern laboratories, sophisticated machines, or advanced analytical tools. It began in a remote land where dark, overlooked rocks lay abandoned along a cold coastline in a small village no one at the time believed would become the birthplace of one of the most important chapters in material science. That place was in Scandinavia, and a single unremarkable stone there would change the world. We will travel there in the next part of the story. On the world map, there are places so small that even if you zoom in all the way, you still have to lean closer to see them clearly. Ytterby is one such place, a quiet Swedish village resting against a dark pine forest and facing the cold Baltic Sea. At the end of the 18th century, there was nothing remarkable here except a modest quarry where locals gathered stone to build houses and fortify the coastline. No one imagined this place would become the cradle of a scientific chapter that would stretch across centuries. Yet, history is sometimes written from the quietest places. One winter day in 1787, Carl Axel Arrhenius, a Swedish army officer with a fondness for mineralogy, visited the Ytterby quarry. Under the dim Nordic winter light, among the red, gray, and white patches of granite, he noticed an unusual black stone, noticeably heavier, yielding a dark purple-tinted powder when ground, and somehow feeling unlike the others. He had no idea he was holding a missing fragment of the universe. Arrhenius brought the sample back to Stockholm, but he could not determine its composition himself. So he sent it to one of Europe's finest chemists of the era, Johann Gadolin of the University of Turku, now in Finland. Gadolin examined the stone from every angle, heated it, dissolved it in acid, and tested it with every analytical method available at the time. And then, he discovered something no human had ever known. The stone contained a new earth. Earth was the term 18th century science used for unidentified oxides, substances that chemical methods could not break down further. Gadolin named it Yttria, after the village of Ytterby, a place he had never visited. From a single black stone, the world gained the element yttrium, and the doorway opened into a maze that would take more than a century to unravel. But what made the Ytterby sample truly extraordinary wasn't just the presence of yttrium. Its structure was a chest of secrets. Every time chemists believed they had isolated the final element, something new appeared underneath. Each cycle of purification revealed another piece, another unusual element, similar in chemical behavior, yet producing its own colors, reactions, and atomic weight. The stone was like a book with many layers, each layer hiding a different chapter, and only by peeling them away one by one could the story emerge. In the early 19th century, the chemist Mosander took up the torch Gadolin left behind. He suspected that yttria did not consist of a single element. He refined it repeatedly, changing temperature, solvents, and rates of precipitation. And just as his intuition suggested, beneath the original yttria, he found 2 more substances, erbia and terbia. Confusion began even at the naming stage. As scientists separated them, the colors of the solutions prompted renamings, then reversals, then renamings again. Terbia and erbia were nearly swapped for decades. More than one chemist believed they had discovered a new element, only to learn later it was a variation of something already named. Another substance, ytterbia, was isolated soon after, and from ytterbia came ytterbium. 4 elements carrying the same ytter root emerged from one tiny village: yttrium, ytterbium, erbium, terbium. A rarity in the history of science, a small place giving birth to 4 entries on the periodic table. The 19th century witnessed the rise of analytical chemistry. Scientists gained better tools, more stable furnaces, and more precise refining formulas. Yet the paradox of rare earths remained. The more they studied, the more lost they felt inside the labyrinth. At the same time, a quiet race unfolded. European laboratories competed to announce new elements. Each discovery was not only scientific progress, but personal glory, national pride. The periodic table became an unfinished map, and whoever claimed a blank spot inscribed their name into eternity. But rare earths posed a unique challenge. They were too similar. They shared oxidation states, had nearly identical reactions, resisted chemical separation, differing only in subtle shifts of color, solubility, or atomic weight. Isolating them was like trying to separate grains of fine sand with bare hands. There were times scientists thought they had identified a new element, but years later, as purification techniques improved, those elements were erased from history. They were merely mixtures of 2 or 3 rare earths that had not been fully purified. And this complexity explains why it took more than 150 years for humanity to discover and confirm all 17 rare earth elements. From Ytterby, discoveries radiated across Europe: Paris, Berlin, London, Vienna, each city with its own laboratory, each contributing to the rare earth map. Scientists became explorers, not of forests or deserts, but of cloudy test tubes where a single mistake could ruin years of work. Ytterby thus became a symbolic landmark, not because it had the richest deposits, but because it opened an era of understanding. A nameless stone forced humanity to rethink its view of matter. It reminded us that great secrets often hide inside the small, the quiet, the overlooked. And from those first discoveries, rare earths would no longer remain laboratory curiosities. They would soon enter daily life, technology, warfare, and the inventions that reshaped the 19th and 20th centuries. And their first moment of transformation began when artificial light appeared, and humankind started to illuminate its own darkness. While European chemists were still hunched over their laboratory tables, turning over mineral samples from Ytterby and other remote lands, the outside world was changing. Darkness was beginning to meet its first true rival. Gas lamps paved the way for a revolution of light, and that light inadvertently called the rare earths out from the shadows where they had hidden for millions of years. At the end of the 19th century, before electricity truly entered every home, humans lit their nights with gas lamps. To make gas lamps shine brightly enough, people needed a kind of mantle placed around the flame, known as a gas mantle. This was where cerium and lanthanum stepped onto the stage for the first time. Karl Auer von Welsbach, an Austrian chemist, discovered that when cerium and thorium were mixed in a specific ratio and heated, the mixture emitted a white light brighter than any other light source of the era. Gas lamps suddenly glowed as they had never glowed before. Streets, squares, theaters, and train stations across Europe shimmered with new brilliance, and that brilliance didn't come from gold or silver. It came from an element once considered an unfamiliar cousin of the metals people actually cared about. Suddenly, rare earths were no longer laboratory puzzles. They became commodities, and once a material steps out of the lab and into daily life, everything changes. Its value changes. Its pace changes. Demand rises. The world's attention shifts toward elements that only a few decades earlier had seemed to have no practical use. Welsbach didn't stop there. He kept experimenting and accidentally opened a new path, Misch metal, a metal alloy containing lanthanum, cerium, and neodymium. In his hands, it became the spark material for lighters. A small strike produced a sharp flash like metal clashing, allowing humans to carry fire in their pockets, bring it wherever they went. Those flashes, in essence, were the combustion of rare earths. As electrification progressed, these elements traveled even farther. They were used to make heat-resistant glass, to produce the red color in television screens, and to stabilize light in fluorescent lamps. Europium and terbium became the light artists of luminescent devices. When you see a red exit sign in an old building, or the pale green glow of a 1970s television, you're looking at their quiet presence. With small but steady steps, rare earths began threading themselves through every advancement of human civilization. But the most important change was in industrial thinking. Once rare earths proved their unique capabilities in lighting, scientists and engineers began asking, what else could they do? Color, magnetism, heat resistance, durability, electrical conductivity? From that question, a door opened into a new world of material science. By the late 19th and early 20th centuries, magnets became the next frontier, calling rare earths by name. Samarium, a seemingly unremarkable lanthanide, began to reveal its unusual magnetic properties. Not as strong as neodymium magnets that would come later, but powerful enough for military and industrial minds to sense potential. Samarium cobalt became the pioneering material for compact yet strong magnets that could operate under high temperatures, exactly what engines, aircraft, and military equipment needed. And just like that, rare earths didn't just light the world, they helped machines move more efficiently. Looking back at this entire period, we can see rare earths walking out of Yatterby, passing through European laboratories, and appearing in every street, every factory, every public service. From the earliest gas lamps to the emerging technologies of the electrical age, rare earths played a quiet but unmistakable role, making light purer, colors richer, and devices more resilient. This was the preparation for the next era, an era in which the world would plunge into war, and everything that once seemed like gentle, peaceful applications would transform into matters of survival. The elements that lit Europe's streets would soon enter battlefields, reconnaissance devices, radar systems, and night vision scopes. From peaceful light, rare earths would march straight into the years when humanity drowned itself in violence, and there, their true weight would finally be revealed. When the darkness of humanity began to thicken in the early 20th century, the world faced an unavoidable truth. The things once used only to light city streets now had to enter the battlefield. Once humanity hurled itself into the largest conflict in its own history, every technology, no matter how small, was swept into that brutal machinery. And rare earths, the elements that once illuminated gas lamps, became the subtle materials hidden inside the machines that war could not live without. A soldier in World War I didn't carry rare earths in his backpack, but the artillery he adjusted, the binoculars he looked through, the compass he held in his hand, all bore the imprint of elements few people could name. Cerium, once used to spark lighters and flares, became a tool of life and death in the trenches. When cold night fell, a single strike of a cerium flint could mean the difference between a signal of survival and eternal darkness. No one knew that in scraping their fingers to make that faint spark, they were touching an element born from the explosion of ancient stars. World War I ended in blood and mud, but military technology did not stop. Nations understood that the next war would rely not only on bullets and cannons, but on what the eye could not see: radio waves, light, signals, and radar. And to command the invisible, they needed special materials, things that could withstand heat, endure magnetic fields, amplify light, and bend electromagnetic energy at will. So rare earths, like a quiet current, stepped out from the wings and moved toward the center of military secrets. When World War II erupted, radar, the technology that could see through night and fog, became the eyes of the modern army. Early radar systems used special phosphors to display signals on screens. Europium and terbium, once mere strange specks in laboratories, became the beating heart of those screens. Thanks to them, a faint signal in the sky became a small glowing point on a dark background, showing the direction of an enemy aircraft. Rare Earths, for the first time, saw what soldiers could not only radar, but night vision scopes, artillery sights, and navigation devices all relied on special glass made from lanthanum. This glass produced clearer, sharper images that didn't distort in low light. A bullet missing or hitting its target could begin with the precision of that thin layer of lanthanum glass. Layer by layer, rare earths seeped into military technology the way water seeps into stone. In secret laboratories in the United States, Germany, Britain, and Japan, scientists tested the magnetic and thermal properties of compounds containing samarium, praseodymium, and neodymium. Just as gunpowder had transformed the Middle Ages, stronger, more durable, and smaller magnets were poised to transform military engines. Sonar devices under the sea, the Navy's ears, used materials containing rare earths to convert sound and electrical signals with precision. These elements never stood on the front lines, but they lay at the core of machines that could change the fate of a war. That was why governments of the period began to recognize a painful truth. Rare earths were not just industrial materials, they were strategic resources. Classified military reports noted their scarcity, their difficulty to control, and their irreplaceable nature. The more war-accelerated technology, the more obvious the importance of rare earths became. In the first reactors of the Manhattan Project, rare earth elements like gadolinium and samarium acted as neutron absorbers, preventing chain reactions from spiraling beyond control. Without them, scientists would have faced unacceptable risks. In a way, rare earth stood between humanity and the absolute destructive power it was trying to unlock. World War II ended with two explosions that reshaped the global order, but beneath the ash, one truth was carved deeply. Rare earths were weapons without sound, a resource every industrial nation needed, yet few could extract and refine. From here, rare earths entered a new era, one in which science, warfare, and geopolitics became tightly bound together. The arms race was no longer just about guns, submarines, and aircraft. It became a race for materials. Whoever possessed better materials could build sharper technologies. Whoever mastered the technology could shape power itself. When the war quieted, and silence returned to the surface of the world, deep below, in secret laboratories, power plants, and nuclear research facilities, rare earths began writing their next chapter. They would not stop at lights, at radar, at battlefields. They would move into something larger, more dangerous, where even the smallest mistake could make an entire city vanish in a flash. This was the atomic era, and rare earths were about to become the gatekeepers of the most perilous age of the 20th century. When the war had barely ended, the world entered a strange kind of quiet. A quiet not born from true peace, but from machines being designed in the dark. New laboratories rose from the ground, thick concrete bunkers opened their doors, and chemical property charts were spread out across tables. Instead of the sound of artillery, humanity now heard the scratch of pencils on paper, the ticking of measuring devices, the faint metallic chime under a scientist's hand. Everything revolved around one thing: the atom. As nations stepped out from the aftermath of the atomic bombs in Hiroshima and Nagasaki, while nuclear fear blanketed the world, physicists understood something with absolute clarity. To control atomic power, they needed materials unlike anything humans had ever used. Materials that could withstand extreme heat, remain stable under intense radiation, and adjust every tiny step of a nuclear reaction, the way an artist guides a chaotic orchestra of racing neutrons. And in that very moment, rare earths emerged from the shadows like the silent gatekeepers of the atomic age. Inside a nuclear reactor, everything begins with neutrons. Neutrons behave like scattering raindrops. Each one can split a uranium nucleus, releasing energy and creating more neutrons. Uncontrolled, they flare up like wildfire. Controlled well, they become an immense source of power. Gadolinium and samarium, two rare earth elements few people had ever heard of, can absorb neutrons so strongly that they became known as the brakes of the atomic world. A thin sheet of material containing gadolinium placed between fuel rods instantly slows the reaction rate. No sound, no complicated mechanism. Rare earth atoms simply swallow neutrons like tiny black holes. In the first experimental reactors in the United States and Europe, control rods containing rare earths played a decisive role, preventing reactors from surpassing safe thresholds. Ordinary materials could not survive the temperature and radiation, but rare earths could. Their stability made it possible for reactors to run thousands of hours without melting down. This created an odd paradox. Elements born from exploding stars, lying, silent in rock for billions of years, were now what helped humans control the same kind of energy that had once created them. But the role of rare earths did not stop at keeping things safe. In the early years of nuclear weapons research, scientists used various lanthanides to analyze radiation limits, determine neutron density, and study isotope decay. Even details as small as a few millionths of a gram of europium inside a fuel sample could reveal precisely what research teams needed to know. And as the world entered the Cold War, this role became more visible than ever. The United States, the Soviet Union, Britain, France, and China all raced to advance nuclear science and to control countless experiments, test detonations, and reactor developments. They depended on extremely stable materials, ones that could endure the heat of potential annihilation. Rare earths became the material foundation for instruments, sensors, research reactors, and the fine calculations behind strategic weapons. In early nuclear power plants, lanthanum-containing glass was used in radiation-resistant viewing lenses, the lenses operators relied on to peer into the heart of the reactor. Few people realized that to look through that glass was to look through the crystallized form of a supposedly obscure lanthanide. One could say rare earths allowed humanity to step into the nuclear age without being swallowed by the atom's own heat. But the deeper truth lay one level further. This era made nations realize rare earths were irreplaceable, not only for lighting technologies, not only for radar, but for the systems that determined the balance of global power. A nation wanting to develop nuclear energy needed rare earths. A nation chasing advanced military technology needed rare earths. A nation competing in materials, science needed rare earths. And from here, a new rule carved itself into global geopolitics. Elements once lying silent in stone were now the tiny needle turning the strategic compass of the world. As the nuclear race intensified, the world was about to enter another, subtler race, a technological race where every small improvement in materials could create enormous advantages. And that brought rare earths into their next chapter, a chapter no longer defined by pure scientific curiosity, but by competition between two superpowers shaping the world. That race began when an iron curtain was drawn across the globe, and the elements once seen as small and insignificant became the very first bricks in the vast architecture of Cold War power. When the Iron Curtain fell across the world and the planet split into two opposing poles, the air itself felt tightened. The thunder of World War cannons had ceased. Yet this new silence was thicker, heavier, and far more persistent. It was the silence of closed-door meetings, of submarines sliding beneath the ocean floor, of secret satellites drifting in orbit, and of machines humming endlessly inside research facilities stretching from Nevada to Siberia. At the center of that vast picture, rare earths became the one class of materials both superpowers could not live without, yet could not openly name. In the Cold War, the race was not fought with guns. It was fought with tiny atoms, bits of information, radio frequencies, and electronic devices that had to function under the harshest conditions imaginable. All of those required materials have strong magnetism, stable behavior, sophisticated optical qualities, and exceptional heat resistance. Rare earths were the only group of elements capable of meeting all four demands at once. The 1950s and 1960s were years of relentless activity within secret laboratories. Both the United States and the Soviet Union asked the same question. How can we build devices that track the enemy from great distances, under brutal conditions, and for long periods of time? The answer led them to a new material: cobalt-samarium magnets. Samarium, once an obscure lanthanide, suddenly became a protagonist. When combined with cobalt, it formed an unusually strong magnet that retained its magnetism even at high temperatures, something no ordinary magnet could do. Miniature motors inside cruise missiles, guidance systems for torpedoes, naval radar units, and even satellite electronics relied on these magnets for stable operation. A motor no bigger than a palm could determine whether a missile hit or missed its target, and it was the seemingly anonymous samarium atoms that kept that motor calm amid the heat of supersonic velocity. At the same time, laser technology was stepping out of theory and into military use. Neodymium lasers, built upon the light-amplifying abilities of neodymium, became the foundation of long-range distance measurement, targeting, and guidance systems. Every faint red laser beam flickering across a battlefield was the result of thousands of atoms placed in perfect alignment, vibrating at precise energies. Inside American research facilities, the development of magnetic ceramics based on rare earths became an absolute priority. Compounds containing yttrium, europium, and gadolinium created materials capable of carrying microwave signals, absorbing radiation, and stabilizing electronic pulses in sonar and radar systems. These materials formed the very heart of hearing and seeing in modern warfare. A submarine, lost in the pitch-black ocean, could distinguish between the sound of waves and the hum of an enemy engine only because rare earth materials deep within its body absorbed vibrations and converted them into readable electronic signals. And, as an inevitable rule of the age, every time the United States built a new technology, the Soviet Union sought to replicate its own version. Two scientific systems, two economic models, two engines of power, both depended on the same group of elements, not oil, not steel, but elements found in a handful of small ore. Deposits, places where standing at the mine entrance revealed nothing of the materials shaping the future of the world. Yet, this dependence carried a constant anxiety. Neither the U.S. nor the Soviet Union fully controlled the supply. Classified reports from the era show that both superpowers had to import part of their rare earths from third countries, sometimes neutral ones, sometimes from unpredictable partners. The fear wasn't only scarcity, it was the lack of purity. Separating and refining rare earths was so complex that only a few nations could do it at scale. Despite being wrapped in political slogans, both blocs understood a simple truth: whoever mastered materials technology would master the game. During the Cold War, a new map emerged, not a map of borders, but a map of resources, which mines contained monazite, which held bastnasite, who had refining technology, who could secure their supply chain. Rare earths became the hidden body of the iceberg of power, unseen, yet determining the direction of the entire frozen mass. As the confrontation stretched over decades, war no longer took place only on land or in the sky. It moved into space, and the first satellites orbiting the Earth, silently sending signals back to command centers, carried rare earths in their cores, from ion engines to sensors, from reflective mirrors to control systems. The story that began in Ytterby passed through Europe's laboratories, lit the streets of growing cities, and entered the battlefields of world wars, revealed its full strategic meaning only in the Cold War. These elements had become the keys to measuring, tracking, guiding, calculating, and sustaining the delicate tension between two superpowers. Though no one mentioned them in speeches, rare earths stood behind the most dangerous moments of the 20th century. And as the U.S.-Soviet confrontation expanded into space, rare earths began a new journey as well, a journey upward toward the sky, where humanity would see the Earth from the outside for the first time. When humanity first looked up at the sky and saw the Sputnik satellite glide overhead, the world suddenly understood that the boundaries of the technological race had changed forever. From that moment on, progress would no longer happen only underground or in laboratories where scientists bent over glass tubes. The next steps would take place beyond the atmosphere, in a cold void where ordinary materials became brittle, weak, or warped. And if we wished to send machines into space, the materials had to be different. They had to resist cosmic magnetic interference, endure the burning radiation of the sun, and survive temperatures hundreds of degrees below zero without shrinking or cracking. Once again, the world returned to the answer hidden in tiny atoms that had once lain silent inside stone: rare earths. Their presence appeared in the earliest satellites. In sensors, rare earths amplified the faintest signals from space. In control systems, they formed the essential components of actuators, the devices that could turn weak electrical impulses into precise mechanical movements, allowing satellites to hold their exact position in orbit. But the most extraordinary role of rare earths in this era was found in ion engines, the beating heart of many space probes. Ion engines do not burn fuel in the traditional sense. They propel spacecraft by accelerating millions of ions at extremely high velocities. To do this, they require materials capable of emitting electrons with stability and endurance. Cerium and lanthanum, the same elements that once lit Europe's gas lamps, now formed the foundation of engines that would drive spacecraft to distances no human had ever imagined. In the silent darkness of space, where there is no sound and no weight, rare earths became the legs of humanity. This transformation grew even more profound when humans launched the first satellites capable of observing Earth and neighboring planets. The optical systems aboard these satellites required a special kind of glass, transparent, radiation-resistant, and able to maintain its shape while temperatures swung across hundreds of degrees. Lanthanum, an element few people recognized, became the key to creating this glass. Thanks to it, the enormous windows on space stations and probes did not warp, crack, or shatter when one side faced the burning sun while the other froze in shadow. The vivid color images NASA sent home, from the surface of Mars to the swirling clouds of Jupiter, all passed through glass containing rare earths. During the same period, neodymium lasers entered distance measurement devices and orbital navigation systems. By sending a laser beam outward and measuring its return time, satellites could determine their position in orbit with near-perfect accuracy. And every time that hair-thin beam was generated, millions of neodymium atoms oscillated at a single precise frequency, a level of synchronization so exact that even a millionth of a deviation was unacceptable. Even in the memory systems of early spacecraft computers, rare earths were present. Certain rare earth compounds stabilized information in high radiation environments where normal silicon chips would fail easily. When Apollo 13 experienced its crisis, when the Voyager spacecraft traveled into interstellar space, and when the Hubble telescope sent back its majestic images of the universe, rare earths quietly stood behind it all. There is something poetic in this. Billions of years ago, when a star exploded and created rare earth elements, they drifted through the infinite cosmos. And then, when humans finally invented the technology to reach space, those elements returned to the very place where they were born, only now carrying the intelligence and dreams of an entire species. In a sense, rare earths are humanity's material passport to leave Earth. But the journey into space was only one, part of a much larger picture. During the same era, another silent shift was happening on the ground. The global supply of rare earths was changing, production was shifting, and the balance of material power was beginning to tilt in a direction almost no one noticed. While the world kept its eyes on the sky, deep underground, a major North American mine was preparing to shut down, and across the globe, another nation was quietly building what would become the geopolitical weapon of the 21st century. We will see this more clearly as we step into the next stage of the rare earths journey. In the late 1970s and early 1980s, while the space race still carried the fading heat of the Cold War, a quiet event unfolded in the western United States that almost no one noticed. In the Mojave Desert of California, the Mountain Pass mine, once the pride of the Western rare earth industry, began to slow down. The familiar assembly lines that had run for decades grew silent. The grinding of stone became infrequent. The warm yellow lights of the processing buildings turned off earlier each evening. From a distance, no one could imagine that this silence would create a void so large that the entire world would later have to revolve around it. Mountain Pass had once been the largest producer of rare earths on Earth, especially bastnasite, the key supply for optical technologies, magnets, lasers, and electronic components after World War II. But rare earth mining was never a clean job. During production, large amounts of waste containing thorium and uranium, naturally radioactive elements, were released into the environment. The cost of cleanup, treatment, and meeting U.S. environmental standards kept rising. One day, people realized that every pound of rare earths came with an environmental and financial price too high to justify. At the same time, the cost of producing rare earths around the world began to shift, not because of technology, but because of another force. While the dry winds of the Mojave Desert continued to blow across Mountain Pass, half a world away, a nation was quietly planting the first seeds of an industry that would later make the entire world dependent on it: China. In the 1980s, China had not yet become an industrial superpower, but it possessed something the global powers lacked: enormous rare earth reserves in Inner Mongolia, Sichuan, and Guangdong, along with inexpensive labor and lenient environmental regulations. More important than any of this, China possessed something the West was losing at that moment: the determination to build an entire value chain, from extraction to refinement. Mining rare earths was not the challenge. Refining them was. Ore containing a dozen different elements had to pass through dozens of steps: chemical separation, ion exchange, precipitation, calcination, filtration, washing, before becoming a product pure enough for industry. This was the step Mountain Pass had to spend millions of dollars to handle safely, while in other parts of the world, that cost simply did not appear in the price tag. And China understood this. Quietly but steadily, China expanded its refining facilities in Baotou in the north. Small workshops appeared. Pools of dark green waste mud spread at the feet of ore processing buildings. Chemical smells drifted faintly through the air. All of it formed the crude but effective foundation of a new industry: large-scale rare earth refining. Meanwhile, in the United States, every environmental requirement, every new regulation, every minor leak added another burden to Mountain Pass. Eventually, the mine was forced to partially shut down, and years later, it was nearly shut down entirely. On the world map, it looked like a small dot disappearing. But in reality, it was the moment the river of strategic materials changed direction. From the late 1980s onward, cheap rare earth exports from China flooded the global market. Manufacturers of electronics, motors, lasers, spare parts, and components gradually shifted to Asian supply because the prices were simply too low to refuse. And when prices plummet, industries in other countries lose their incentive to keep their own production alive. No one worried. These elements sounded too distant, too abstract to matter in daily life. No one imagined they would become the choke point of the global supply chain decades later. In the eyes of many at the time, rare earths were just a minor mineral serving a few narrow industrial sectors. But the truth lived beneath the surface of the numbers. Within a few years, China not only became the world's largest rare earth miner, but also its dominant refiner, the most difficult, most knowledge-intensive, and most value-defining stage of the entire supply chain. The small, modest refineries began expanding, lengthening production lines, and upgrading technology. Chinese scientists poured effort into mastering sophisticated separation techniques once performed only by the United States, Japan, and Europe. In a world growing increasingly dependent on electronics, one nation was beginning to control the foundational materials behind them. No one at Mountain Pass could have imagined that the quiet pause of a desert mine would mark the beginning of a new center of power. No one expected that simple signs reading "temporarily closed for maintenance" would become milestones in a future where global economies would have to pivot, turning toward the east in search of supply. The elements born from stardust, once separated by hand in European laboratories, once hidden behind wartime radar and the first ion engines, were now drifting into the hands of a nation preparing to reshape the future of global technology. That journey would go even further when one Chinese leader would speak a sentence that made the entire world pay attention, the moment rare earths officially stepped into geopolitics. And that sentence lies just ahead. In the late 1980s, while much of the world still viewed rare earths as a faint, insignificant corner of the periodic table, China saw something else in them, a different future. A future in which materials, not oil, not steel, not coal, would determine the map of global power. And in that seemingly quiet moment, a sentence was spoken, light as a breath yet sharp as a blade, slicing straight through the industrial age. The Middle East has oil, China has rare earths. Deng Xiaoping. It was not a speech, not an official announcement, just a single sentence, but enough to lay the foundation for an industrial strategy spanning decades. In that sentence, Deng Xiaoping did not describe a present reality. He described a vision: to turn rare earths into China's new oil, because he understood clearly that in the century to come, it would not be fossil fuels, but advanced materials that determined technological advantage. While many countries rich in rare earth minerals still treated them as secondary resources, China began doing what no one else had done, building the entire value chain from start to finish, not just mining, not just refining, but owning the technology to produce high-strength magnets, display phosphors, heat-resistant alloys, laser materials, electronic components, motor magnets, compounds for batteries and precision devices. In the late 20th century, the concept of a complete supply chain was still new. But for rare earths, China understood that simply owning the mines did not grant power. Power lived in refining, in material fabrication, and in making intermediate products. The steps requiring chemical knowledge, engineering expertise, and massive capital investment. Unlike many nations, China did not attempt to sell raw ore and hope to profit from mineral prices. It built hundreds of research institutes, harnessed inexpensive technical labor, accepted enormous environmental costs, and constructed a refining capacity no competitor could match. In Baotou, Inner Mongolia, an industrial expanse rose from the ground. Wastewater ponds stretched out, colored the dark green of chemicals. Chemical reactors ran 24 hours a day. The air carried faint traces of acid. To outsiders, it looked like the harshness of heavy industry. Inside, it was the beating heart of the global technology supply chain. Tons of monazite and bastnasite ore entered the pipelines. Hundreds of thousands of liters of solvent were used to separate each element. Drops of perfectly purified solution were passed to the next workshop. From there, they became small metal ingots, or white, yellow, pink, and pale blue oxide powders, each color representing a different technological future. When Japanese, Korean, and American electronics companies sought cheap and stable raw materials, China was ready. Rare earth prices were so low that no country could compete. Magnet manufacturers in the United States, Europe, and even Japan gradually became dependent on Chinese supply. And the turning point came when the global economy entered the age of mobile phones, laptops, thin screens, high-efficiency motors, and new energy technologies. The more devices the world produces, the more rare earths become its bloodstream. And that bloodstream flowed almost entirely through China. Every phone required europium and terbium for its display. Every electric vehicle motor needs neodymium magnets. Every wind turbine requires dysprosium to withstand heat. Every stealth aircraft used yttrium in high-temperature alloys. Every navigation system depended on neodymium lasers. Every satellite needed special ceramics containing lanthanum. And for each of those needs, China had already built a link in the supply chain. As the global economy shifted into the digital age, China did not merely join the game, it became the player holding the most critical pieces. Deng Xiaoping had seen what the rest of the world had not. Rare earths would not remain chemical curiosities, they would become levers of power. From the late 1990s through the early 2000s, Chinese rare earth exports dominated the world, while Western mines closed or shrank under overwhelming costs. The shift from Mountain Pass to Baotou was not a dramatic moment, but a slow, steady current leading to the day when the whole world suddenly realized, to manufacture technology, they must look to China. To build phones, they must look to China. To develop modern weapons, they must look to China. To shape the future of green energy, they must look to China. A sentence once spoken became a prophecy. The Middle East has oil. China has rare earths. And that prophecy would soon lead the world into a moment of tension where demand surged, supply tightened, and these silent elements turned into one of the most critical political issues of the 21st century. Before we reach that point, we must understand the technological explosion that carried rare earths from geology into the heart of every smart device. And that is the door to the next chapter. As the world entered the early 21st century, every motion changed its speed. People looked down at their palms and saw a device that could call, record, photograph, navigate, calculate, remember, all within something smaller than a pocket notebook. But this miracle was not born from magic, nor from software alone. It came from materials, from elements no one sees, no one hears, no one mentions in daily life. The smart world we live in today is built from rare earths, quite literally. Imagine a smartphone. Beneath the glass screen, thin as breath, hundreds of tiny components operate ceaselessly, and almost all carry the fingerprints of rare earths. The vivid red of an LED display comes from europium. The cool green glow comes from terbium. A stable white phosphor made from yttrium blends these colors into a complete image. The camera captures light because lanthanum-based glass keeps distortion so low that the human eye cannot detect it. Image stabilization works because neodymium magnets keep the tiny motors steady with every vibration. A smartphone smaller than your palm may contain 8 or 10 different rare earth elements, and not a single one can be easily replaced. But phones are only the tip of the iceberg. The world is moving faster, and every motion requires strong magnets. Neodymium, combined with praseodymium and dysprosium, forms permanent magnets powerful enough that even a small piece can spin an electric vehicle's wheels at high speed. That is why EV motors can shrink, lighten, become more efficient, consume less energy, and run far quieter than traditional engines. If the world wants cleaner air and less noise, the heart of every electric car, the permanent magnet motor, is built from rare earths. When night falls, millions of headphones come to life. Inside them, neodymium magnets make the devices compact yet powerful, reproducing sound that is deep and clear. In hard drives, read-write heads rely on rare earth magnets to stay stable at extreme rotational speeds. Even the smooth, silent opening and closing of a laptop hinge comes from rare earth magnets. A detail so small it seems trivial, yet it makes computers thinner, lighter, and more durable. The entire digital world depends on elements where just a few kilograms can determine whether a device is exceptional or merely adequate. But rare earths did not write this chapter alone. The explosion of technology triggered an explosion of demand. As smartphones became inseparable from billions of lives, as TVs shifted to LED, as laptops grew ultra-thin, speakers became more powerful, batteries became smarter, and the technologies behind them accelerated. Japan needed rare earths for Sony, Panasonic, and Toyota. South Korea needed them for Samsung and LG. The United States needed them for Apple, Boeing, and Lockheed Martin. Europe needed them for Siemens, Philips, and Airbus. Each year, demand grew. Each year, the world's dependence deepened. Each year, rare earths become more like the nervous system of the global economy. And as humanity consumed more smart devices, the scope of rare earth applications widened. Sensors in smartwatches, image stabilization in cameras, ultra-durable ceramics in phones, GPS navigation systems, satellite communication chips, fiber lasers for industrial manufacturing, supermagnets for autonomous robots, high coercivity magnets for military drones. All of these require rare earths, no exceptions. But the deeper truth was this: the very technological boom that lifted the world also revealed something impossible to ignore. The entire planet was becoming almost completely dependent on a single source. China was no longer just exporting raw, rare earth ore. It was exporting refined materials, magnet alloys, display phosphors, and metal oxides with 99.9999% purity. Products without which the manufacturing lines of phones, laptops, TVs, headphones, drones, electric vehicles would halt instantly. Once the digital world began accelerating, the rare earth supply chain stopped being simply an industrial matter. It became a geopolitical question. If one nation can control the foundational materials of the world, can it control the world's future? And that question leads directly into the next chapter, where rare earths step into a realm long hidden in the shadows, yet central to national power: the military. As civilian technology entered its explosive phase, the military world did not stand outside that current. In fact, one could say the military has always been the first place where new materials are tested, pushed to their limits, and used under conditions where even the smallest error can bring irreversible consequences. And in the late 20th century, no group of elements became more of a backbone of defense technology than rare earths. These elements that once lit old gas lamps, once sat quietly in the laboratories of Scandinavian chemists, now stepped into the center of the most sophisticated machines humanity had ever built for war. The sky was where rare earths showed their strength most clearly. When the F-117 or B-2 stealth aircraft glided across the air, their shapes all but disappeared from radar screens. To achieve this, beyond angular aerodynamic design and radar-absorbing coatings, there was a secret buried deep inside the metal structure: alloys containing yttrium, lanthanum, and neodymium. These elements allowed structural materials to tolerate extreme heat, resist oxidation, and withstand deformation while flying at high speeds through scorching air. Inside the cockpit, sharp, stable displays operated thanks to phosphors made from europium and terbium, materials capable of maintaining color integrity under constant vibration and fluctuating pressure. But that was only the surface. The more crucial role lay in the heart of active electronically scanned array, AESA radar, the technology that allowed modern militaries to see farther, sharper, and more precisely than ever before. Each microwave amplifier, each signal filter, each wave-guiding layer relied on rare earth compounds to maintain stability across temperature extremes and intense operational conditions that ordinary components could never endure. If radar is the eye of a modern aircraft, rare earths are the exquisite lenses that let that eye see through darkness. Along the boundary between water and the deep shadow of the ocean, submarines entered the story with a completely different requirement: silence. A single stray sound could cost the lives of an entire crew. Inside a submarine, sonar is its most crucial weapon. It allows the vessel to hear and see with sound, and those sonar systems, from piezoelectric sensors to acoustic transmission materials, rely on rare earth elements like neodymium, samarium, and gadolinium. A conventional propeller produces loud mechanical noise, but permanent magnet motors made from rare earths reduce that whine to near silent levels. This is why newer submarine generations are far harder to detect than their predecessors. As a submarine moves beneath the sea, its survival depends on distinguishing a harmless collision of waves from the distant churn of an approaching propeller. That distinction is made possible by elements that exist at only a few parts per million in natural minerals. On land, tanks and air defense systems also relied on rare earths for night vision targeting. Night vision optics used glass mixtures containing lanthanum, erbium, and neodymium, materials capable of amplifying faint light into clear images. Laser guidance systems, rangefinders, and ballistic computers all contained optical or magnetic components derived from rare earths. In missile defense systems, rare earth magnets played a critical role in control mechanisms. These systems required near absolute precision, and any deviation could send a missile off course. Neodymium and dysprosium, the same elements used in electric vehicle motors, were also the materials that allowed missiles to alter direction within thousandths of a second. But perhaps the most important part of this chapter is not the individual devices, but the new shape of warfare itself. If World War II was a war of steel and fuel, modern warfare is a war of optics, magnetics, electronics, and signals. And rare earths are the only material group that connects all four at once. A surveillance drone can fly for tens of hours thanks to rare earth permanent magnet motors. A missile defense system can identify targets using optical sensors containing lanthanum. A high-frequency radar can maintain signal stability with yttrium iron compounds. A stealth aircraft can withstand extreme heat thanks to alloys containing rare earth elements. It is no coincidence that classified reports from the United States, Europe, and Japan during this period repeatedly stated, "Without rare earths, modern military power would be cut in half." This was not an exaggeration, it was material science. And this truth paved the way for a new era of tension. As warfare changed shape and the world moved toward clean energy, rare earths would not only be a military material, but the foundation of the coming energy revolution. A revolution celebrated as green. Yet its foundation, as we will see, carried the gray, murky color of chemicals, waste ponds, and ever-expanding mines. That door opens in the next chapter. The dawn of the 21st century was given many names: the green era, the renewable era, the era of energy transition. People spoke of wind, of sunlight, of roads without the roar of combustion engines, of cities where the sky remained clear as freshly wiped glass. But as the world stepped into that new age, a paradox emerged. To reach the color green, humanity had to pass through thick shades of gray, and rare earth elements formed the foundation of that path. Across wind fields in Denmark, Scotland, China, the United States, massive turbines rotated slowly but steadily. Each turn delivered another pulse of clean energy into the grid. Yet inside the core of every turbine, where heat and mechanical strain reached extraordinary levels, were permanent magnets made from neodymium, praseodymium, and especially dysprosium. These elements could endure temperatures that would instantly demagnetize ordinary magnets. Modern wind turbines could stand as tall as a 20-story building, with blades longer than the wings of a commercial airplane. And it was rare earths that kept them standing against storms, strong winds, and the endless shifting moods of the weather. Without rare earths, wind energy would be weak, intermittent, and unstable. Without rare earths, the green future would remain nothing more than an unshaped promise. On the streets, electric vehicles glide by in near silence. The air is cleaner. The harsh sound of combustion engines has faded. But inside each EV, from Tesla, BYD, VinFast to Nissan and Hyundai, lies a heart made of rare earths. Permanent magnet motors use neodymium and praseodymium to generate high force in a compact size. To keep the motor stable under high heat, especially during fast acceleration or uphill climbs, dysprosium is added to preserve magnetism. Every smooth rotation of the wheels, every surge of acceleration, every quiet pulse of an EV is powered by atoms smaller than dust. The world celebrates electric vehicles as the future. Yet few know that an average EV contains about 1 kilogram of rare earths, enough to keep an entire industrial plant busy for weeks. Not only the motor, but many other EV components rely on rare earths. Control screens, europium, terbium, speakers, neodymium magnets, LiDAR sensors, optical rare earths like erbium, power converters, yttrium-based compounds. A vehicle may look clean, but its journey from mine to factory carries the heavy gray of chemical refining. Solar power, the seemingly purest form of light, also relies on rare earths to maximize efficiency. Some next-generation solar technologies use special coatings containing lanthanum or cerium to enhance absorption and reduce thermal loss. In the transformers that connect large solar farms to the grid, rare earth magnets optimize power transmission. Even in energy storage systems, the heartbeat of the green economy, rare earths remain central. Nickel metal hydride batteries, large industrial batteries, and many rechargeable systems use misc metal containing lanthanum. The power grid of the future, where millions of homes receive energy from wind, sunlight, EVs, and charging stations, cannot function without rare earth magnets to stabilize current and reduce energy loss. But here is where the AT paradox becomes sharpest. The world speaks of clean energy, yet the process of creating materials for clean energy is anything but clean. The deep green waste ponds of Baotou in Inner Mongolia, the bright red open-pit mines in Sichuan, the acidic sludge rivers running through Myanmar's valleys. These are the real costs of the Green Revolution. To obtain a single pure neodymium magnet, one must grind tons of ore into fine powder, use acid to separate all 17 elements, filter repeatedly dozens of times, calcine at high temperatures, combine with other elements to form an alloy. All these steps produce waste sludge containing thorium, uranium, fluorides, substances that, if mishandled, can poison entire regions for decades. For every electric car on the road, hundreds of liters of wastewater are discharged from refining processes. For every wind turbine erected, somewhere a piece of land has been dug down tens of meters. For every new smartphone, fresh ore is torn from the Earth's crust. The Green Revolution, seemingly separate from heavy industry, is in fact built upon it. Only the smokestacks and waste have been pushed far from the eyes of consumers. Yet this paradox does not slow the world down. On the contrary, it creates an even deeper dependency. The greener humanity becomes, the more it needs rare earths. The more sustainable the future aims to be, the more the world must confront the truth that the foundational materials of tomorrow are difficult to mine, refine, or replace. And amid this rising dependency, the world gradually realized that with a single adjustment of rare earth supply, by raising or cutting exports, one nation could shake the entire global energy sector. That moment has already happened, and the world trembled. There are moments in history when the world is moving along a familiar trajectory and then suddenly veers sharply in a new direction because of a change that seems small. The year 2010 was one such moment. A single export decision, a tightened quota, a gate closing in the East, and the entire global technology supply chain shuddered. It would be difficult to grasp the shock of that year without looking back at the context. For many years in a row, the entire world relied on cheap rare earths from China. The neodymium magnets in Toyota Prius electric motors, the phosphors in plasma TVs, the laser amplifiers in factories, the components in radar, missiles, hard drives, cameras, all came from tens of thousands of containers of rare earths shipped out of Chinese ports every year. Manufacturers in the United States, Japan, and Europe had grown so accustomed to that stability that they no longer thought about backup plans. Mountain Pass had closed, plants in Australia had scaled down. Many nations with large reserves, such as Vietnam, India, and Brazil, still lacked deep refining capacity to join the value chain. Then came the autumn of 2010, a collision between a Chinese fishing boat and a Japanese patrol vessel near the Senkaku Islands sent relations between the two countries to rock bottom. No gunfire, no declaration of war, just a minor maritime confrontation. But from Beijing, a signal was sent. China tightened rare earth exports. There was no official announcement declaring a full halt, but dozens of Japanese companies simultaneously reported that their containers of rare earths were not being cleared through customs. Export quotas were slashed, export taxes increased, customs controls tightened, and within weeks, the global market realized that what Deng Xiaoping had said 3 decades earlier was not just a prophecy, it had become reality. Rare earth prices skyrocketed exponentially. Neodymium, up 10-fold, europium, up 20-fold, terbium, up 30-fold, dysprosium, nearly 40-fold, a surge that crippled many industries. Japanese technology corporations, heavily dependent on rare earths for cameras, hybrid batteries, and TV displays, went into panic. Production lines were curtailed, factories cut shifts, component prices spiked. Some companies had to sign procurement contracts at prices unprecedented in history. No explosions, no toxic gas, no military invasion. Yet, the industrial world was paralyzed by a subtle squeeze in commodity exports. What shocked the world was not that China could cut supply, but the degree of absolute dependence that everyone realized only when it was too late. No country, not even the United States or Japan, the leading technology economies, still possessed full-scale refining and processing capabilities. The rare earth industry had globalized in a very particular way. Every pipeline flowed toward China, and when one valve tightened, the whole system trembled. But the 2010 crisis revealed an even deeper truth. The problem was not the ore, but the ability to refine it. The United States had Mountain Pass, Australia had Mount Weld, Vietnam had large reserves in Lai Chau, and Lang Son, Brazil, India, and South Africa all had rare earths. Yet nearly every nation lacked refineries, the hardest, dirtiest, and most expensive stage. More importantly, they lacked decades of experience in separating each element, lacked long-term chemical process data, and lacked complete supply chains to bring high-purity oxides into advanced material production. Meanwhile, China not only possessed refineries, but also controlled the factories that produced permanent magnets, LED phosphors, heat-resistant alloys, the hinges of the entire technology sector. This was why, even as rare earth prices surged, few countries could seize the opportunity to enter the industry. They did not lack resources, they lacked the knowledge and industrial capability. The 2010 crisis woke the world. For the first time, major powers realized that rare earths were not secondary minerals. They were strategic assets, woven deep into every future technology sector. Japan immediately signed multi-billion-dollar agreements with Australia to develop the Mount Weld mine and the LAMP processing plant. The United States restarted Mountain Pass after years of closure. The EU added rare earths to the critical raw materials list. South Korea established an investment fund to stockpile rare earths. Global companies began researching dysprosium-saving technologies, redesigning motors, even seeking substitute materials, though few materials could match rare earth performance. But the truth remained unchanged. Even as the world began searching for escape routes, no one could leave China overnight, because the entire refining value chain had become deeply embedded in global manufacturing. The 2010 crisis was not just an economic shock. It was a warning that in the 21st century, a nation does not need tanks or fleets to shape power. Controlling a handful of small elements is enough to shake technological superpowers. And from that moment onward, rare earths were no longer an industrial issue. They became a strategic issue, leading into the next phase where geopolitical competition over magnets and high-tech materials would become fiercer than ever. After the shock of 2010, the industrial world felt as if it had just awakened from a long sleep. Nations began reviewing their supply chains. Technology corporations inspected every component, every material, and discovered an uncomfortable truth. Most of what keeps the modern world running depends on magnets. But not just any magnets. The strongest, most stable, smallest, most efficient kind, rare earth magnets. And among the rare earths, 4 elements hold critical importance: neodymium, praseodymium, dysprosium, and terbium. Without these 4 elements, electric vehicles would weaken, wind turbines would lose efficiency, drones wouldn't fly far, radar would lose accuracy, hard drives couldn't read data, industrial robots would slow down, and the entire digital world would feel as though its mechanical heart had stopped beating. The key point is that magnet production, not rare earth mining, is the true power lever. People can mine rare earths in the United States, Australia, Vietnam, Canada, but turning rare earths into high-performance magnets is something almost only China can do at scale. And this, precisely, is where 21st century geopolitics finds its new fulcrum. To understand why magnets are so important that they can tilt the global balance of power, one must look at how they work. A neodymium magnet the size of a pea can generate more force than a ferrite magnet the size of a palm. This allows motors to become small, light, quiet, yet astonishingly powerful. Electric vehicles can accelerate faster, drones can fly longer, industrial robots can become more precise, medical devices can be more refined, militaries can develop weapons that are lighter but stronger. In the world of technology, the smaller the device, the more energy it saves. The more power it outputs, the more rare earth magnets become the indispensable material. But dysprosium and terbium, the elements that allow magnets to withstand high temperatures, are extremely difficult to separate and far scarcer than the rest of the lanthanide group. Not every country has suitable reserves, and not every mine can refine them without severe environmental challenges. When rare earth oxides became commodities, neodymium magnets became super commodities, coveted by every high-tech industry, yet producible at scale by only a handful of nations. After 2010, China was no longer just a seller of raw, rare earths. It controlled the entire downstream chain, producing high-purity oxides, metallurgical processing into metals, manufacturing NdFeB alloys, pressing, sintering, and shaping magnets, crafting finished magnets for motors, speakers, robots, and radar. Around 80–90% of the world's rare earth magnets come from China, a number enough to make any industrial economy uneasy. Meanwhile, the United States and Japan understood that the issue wasn't mining more, but reclaiming magnet-making capability, something they had abandoned while chasing cheap costs for 3 decades. Japan began rebuilding alloy production lines. The United States funded research into dysprosium-saving materials. Europe drafted a roadmap for strategic material autonomy. Australia sought to expand separation plants. South Korea invested in robotics and magnet simulation technologies. But the technical gap had grown too large to close within a few years. Because to produce a finished magnet, one needs dozens of skills. Mastery of chemical refining, control of crystal structures, precision over temperature and pressing force, trace element analysis, molecular simulation, and thousands of hours of operational experience. These things cannot be bought. They must be accumulated through time, trial, failure, and refinement, exactly what China had done for 30 years. From a geopolitical perspective, this is what most troubles major powers. A country may have mines, a country may have money, but if it cannot manufacture magnets, it still cannot produce high-tech products. In the modern world, whoever controls magnets controls technology, and whoever controls technology controls power. This is why U.S. strategic reports from 2013 to 2020 repeatedly referred to rare earths as a national security choke point. The Pentagon listed neodymium, praseodymium, dysprosium, and terbium as resources without which the U.S. military could not operate. And it is also why Japan, for many years, built its own strategic stockpile, like stockpiling oil, but for rare earths and magnets. The material war has never been overt. There were no declarations, no fiery sanctions, but a silent front has formed among nations, where every new mine, every new refining plant, every new magnet production line is seen as part of a global power struggle. And while industrial nations search for ways to build autonomy, a new question emerges. Which place could become a counterweight to China? Which place has the reserves, the geopolitical position, and the potential to enter this arena? A few nations have begun to stand out: Australia, Canada, the United States, and especially Vietnam, a country with large reserves but not yet deeply involved in refining. That path will lead the world into the next phase, where every nation seeks to reclaim control, where billion-dollar investments are poured into the earth, and where competition begins to take the shape of a global value chain reconstruction. After the shockwave of the 2010 rare earth crisis, the industrial world realized it had wandered far too deep into a maze without a map. For decades, nations had traded industrial self-sufficiency for low costs and fast production. They had allowed the refining, metallurgy, and magnet manufacturing stages, the most critical links, to drift toward China, because doing so made products cheaper, faster, and more competitive. But when a single link was tightened, the entire global machine shuddered, and that was the moment nations began to examine their own material map. The world understood that it could not reverse the past overnight, but it could begin a long journey, rebuilding the rare earth value chain, from mining to refining, from metallurgy to advanced materials, and ultimately to high-performance magnets. It is a complex, expensive journey, but one that can no longer be delayed. Australia, the first brick of a new supply chain. Australia possesses an advantage few nations have: the Mount Weld mine, one of the richest rare earth deposits in the world, with far fewer impurities than most other sources. When the 2010 crisis erupted, Australia's Lynas became the focus of global attention. Lynas did not merely mine ore, they did something more important. They built the lamp refining plant in Malaysia. This became the largest rare earth refinery outside China. A bold step, because refining was precisely the stage the West had abandoned for 3 decades. Each ton of Mount Weld ore was refined into high-purity oxides, then exported to Japan, a country urgently seeking escape from absolute dependence. For years, Japan became the largest investor in Lynas, not for profit, but for material security. Thanks to Lynas, the world gained a small but steady supply, the first brick in the future's material security wall. The United States, awakening Mountain Pass. The United States once led the world in rare earths, then lost everything when Mountain Pass shut down. But after 2010, the U.S. understood that national security could not depend on a supply chain outside its borders. Mountain Pass was restarted, the plant was upgraded, waste processing technology was standardized, but the U.S. still lacked the most important part: refining technology. Mountain Pass could mine and produce mixed rare earth oxides, but separating them into individual elements, neodymium, praseodymium, terbium, dysprosium, still required sending the semi-processed material to China for final refining. A harsh truth. Even with Mountain Pass revived, the final stage of the rare earth chain remained in the hands of a geopolitical rival. This pushed the U.S. to invest heavily in new materials research, cooperate with Japanese, Korean, and European firms, and rebuild refining capabilities. The Pentagon funded hundreds of millions of dollars for magnet manufacturing companies. States like Texas and Colorado began constructing new metallurgical plants. The road remains long, but America has begun walking. Canada. Vast resources, deep potential. Canada holds numerous rare earth deposits across its expansive territory. Its advantage is not only in resources, but also in political stability, transparent law, and strong international partnerships. Projects like Nechalacho, Strange Lake, and Hoytus Lake began attracting investment from Europe and Asia. Many nations looking to build cleaner, more sustainable supply chains saw Canada as a natural destination. But Canada faced the same obstacle as the U.S. It lacked industrial-scale refineries. Without refining, ore remains only ore. Vietnam, great potential, awaiting the right map. Vietnam often ranks second or third among countries with the largest rare earth reserves. Lai Chau, Lang Son, Yen Bai. All have promising deposits. But potential does not turn into strength without refining technology, an industrial supply chain, and a long-term strategy. Vietnam stands today where China stood 3 decades ago, rich in resources, but without deep processing. This is a challenge, but also an opportunity if guided properly. Technological cooperation with Japan and South Korea, attracting investment to build refining plants, joining the NDFEB permanent magnet supply chain, training engineers, and developing materials laboratories. If Vietnam follows the right roadmap, it could become a crucial link in the non-China rare earth supply chain, something the world urgently needs. Rebuilding the value chain, long, costly, but inevitable. Reconstructing the rare earth chain is not just mining. It is an entire journey with multiple layers: surveying reserves, building ore separation facilities, refining individual elements, producing metals and alloys, manufacturing magnets, phosphors, technical ceramics, developing materials laboratories, training engineers and researchers, building an industrial support network. Every link requires massive investment, long timelines, and patience. China spent 30 years doing this. Other nations are only just beginning. But the driving force is no longer profit. It is national security, technological security, and energy security. as electric vehicles demand tens of millions of new motors. Annually, as wind power needs hundreds of thousands of new turbines, as AI, robots, drones, and satellites require stronger materials, rare earths are no longer optional but mandatory. The world has begun rebuilding its system. But along that process, a harder truth gradually emerges. To supply billions of devices, the world must confront the dark side of rare earths, the impacts few want to look at. That door leads us to the next chapter, the shadowed side of the rare earth industry, where the true cost of technology is revealed. When people talk about rare earths, they often speak of the future: silent electric cars, endlessly spinning wind turbines, brighter screens, smarter robots, more precise weapons. But few are willing to look at the other side of the coin, where rare earths do not carry the image of the future, but the image of a present carefully hidden from view. Because behind every glowing smartphone, every wind turbine blade, every powerful magnet, lie streaks of gray mud, toxic ponds, radioactive dust stockpiles, and communities living on land that has been eroded from beneath their feet. Clean technology, in many cases, begins in places that are anything but clean. The toxic sludge lakes of Inner Mongolia, the forgotten heart of the supply chain, Baotou, Inner Mongolia, the world's largest rare earth hub, is not a place that appears in travel brochures. There sits a massive artificial lake, green-black, spreading across tens of square kilometers, filled with industrial waste sludge. It is not water, but a mixture of acids, solvent residues from ore separation, heavy metal impurities, and naturally occurring radioactive materials like thorium and uranium. Workers here inhale dust particles too small to see. Wind sweeping across the lake carries the smell of chemicals. In winter, a thin layer of ice forms, but beneath it lies a world that never freezes. The accumulation of millions of tons of waste from rare earth refining. Farmlands near this lake once produced grain. Crops still grow, but yields have plummeted. Many families no longer dare use groundwater and must buy water brought from elsewhere because their wells are no longer safe. This is an image most of the world has never seen. Yet, it is the starting point of billions of components inside modern devices, Sichuan and Jiangxi, where rare earth ore is separated in chemical mist. In southern China, the ion adsorption clay, rare earth mines, the easiest type of ore to extract, lie beneath bamboo and pine forests. But extracting them requires tens of tons of ammonium, acids, and solvents. Villages that once sat in lush forests now stand on scarred, patchy land. Wastewater flows through streams and into fields, leaving white chemical streaks on rocks like dried salt at the edge of the sea. In many places, residents say they once had fish in their ponds, vegetables in their gardens, pigs in their stables. But once the mines arrived, everything changed. Some lost crops, some lost land, some lost their health. Not everyone connects persistent coughing, skin lesions, or chronic fatigue to chemicals from rare earth refining. But quiet studies conducted in Chinese universities have documented abnormal concentrations of heavy metals in soil and water around mining zones. Myanmar and illegal rare earth mines, the shadows of the supply chain. When China tightened environmental controls in certain regions, illegal mining shifted across the border into Myanmar. In Kachin State, rare earths are extracted by pumping chemicals directly into the ground, a cheap, fast method that destroys soil structure and poisons water sources. Most workers are poor villagers. No protective gear, no contracts, no air filtration equipment. They live in makeshift camps beside open chemical pools. Mountain streams change color. Fish die. Children develop skin diseases. Villages turn into environmental black spots. Yet the ore continues crossing the border, becoming feedstock for modern refineries. Rare earths go into clean technology, But their journey is far dirtier than most imagine. Africa and South America, a familiar loop, in Madagascar, Tanzania, Brazil. New rare earth projects are being launched. Rare earths themselves are not inherently harmful, but if operations follow the model of extract fast, export fast, leave the environment behind, the history of 20th century mining could repeat itself yet again. Poorer nations are often enticed by short-term profits from raw ore. But without building clean refining capacity and proper waste control, the cost borne by local populations can last generations. Cancer villages, the dark side of convenience. In some local Chinese documents, the phrase cancer villages has appeared with increasing frequency. Small communities where cancer rates are far above average. No one can prove a 100% direct cause, but the link to rare earth extraction and refining, especially when poorly regulated, is difficult to ignore. These are places where children grow up beside discolored streams, where elders remember when the trees were greener, where afternoons in the fields have been replaced by the smell of metal, where rare earths, despite all they mean for the future, leave quiet wounds in the present. The cost no one wants to see. Every electric car glides silently, but somewhere to create that silence there is the sound of ore being crushed, sludge being discharged, and land being torn open. Every wind turbine spins without emissions. But somewhere to create that rotation, acidic wastewater flows. Every bright phone screen glows in your hand. But somewhere to create that light, there's a toxic sludge lake. The question is not, are rare earths bad? The question is, how do we choose to pay for a green future? And that question leads to the next chapter, where the world searches for an exit, a method to reduce harm, a new hope. Rare earth recycling, the quiet technological battle underway in laboratories around the world. For decades, the world saw rare earths as a resource that could only come from the ground. Mine kept expanding. Waste ponds grew larger. Forests were torn open from Southeast Asia to South America. All of it created the impression that the rare earth pathway had only one direction: dig, separate, refine, use, discard. But as environmental anxiety reached its peak, a question began emerging in laboratories. Why keep digging when billions of old devices already contain rare earths? An old phone contains neodymium and terbium in its speakers and display. An old wind turbine can contain over 100 kilograms of NdFeB magnets. Old hard drives contain millions of tiny magnets. Broken EVs, outdated robots, and even household appliances carry large amounts of refined rare earths. So why not recycle them? The question sounds simple, and the world once believed the answer would be simple too. But recycling rare earths is nothing like recycling steel, aluminum, or plastic. Rare earths inside electronic devices do not exist in pure form. They exist inside alloys, embedded in epoxy, mixed with other metals, or locked into components so small they are nearly impossible to separate. To recover neodymium from a tiny magnet, it must go through at least 4 or 6 complex chemical steps, almost the same as refining ore, and each step requires energy, chemicals, and money. Why is rare earth recycling so difficult? In a neodymium iron boron (NdFeB) magnet, rare earths make up only 20–30% of the mass. The rest is iron, boron, and other additives. Separating these components while maintaining purity is a challenge. There are 3 main approaches. 1. Mechanical recycling. 2. Grinding devices into powder, then separating by magnetism. 3. Advantage: fast, cheap. 4. Disadvantage: rare earth output is impure and unsuitable for new magnet production. 5. Hydrometallurgy. 6. Soaking materials in acid to isolate each element. 7. Advantage: high purity. 8. Disadvantage: creates toxic wastewater and sludge unless treated properly. 9. Pyrometallurgy. 10. Heating at high temperatures to separate metals by melting point. 11. Advantage suitable for large-scale volumes. 12. Disadvantage, high energy use and greenhouse gas emissions. No method is perfect. Rare earth recycling demands nearly the same sophistication as extracting rare earths from ore, but yields less value. This is why many countries want to scale recycling but still struggle. High costs, complex technologies, and low throughput. Japan, the pioneer. After the 2010 shock, Japan became the first country to heavily invest in rare earth recycling. Japanese institutes developed techniques to extract neodymium from old hybrid car motors using special solvents. Some companies even collect old hard drives to reclaim their magnets. Yet even with Japan leading, recycled rare earth supply only a tiny fraction of demand, just a few percent. Europe, expanding research and testing circular models. The EU sees rare earth recycling as part of its circular economy strategy. Several funded projects include recovering dysprosium from EV magnets, recovering europium from old fluorescent lamps, extracting erbium from telecom equipment. But the scale is still far too small compared to the exploding demand for EVs and wind power. The United States, a long-term strategy for the future. The U.S. invested in recycling magnets from old hard drives, a field with a stable supply. Tech corporations began collecting old devices not only for environmental responsibility, but also for supply chain security. But like Japan and Europe, the U.S. faces the same economic puzzle. Recycling is too expensive compared to buying refined rare earths from Asia. China, the paradox of dominance. Well, although China dominates global refining, rare earth recycling there remains limited. Reasons include newly mined rare earths are too cheap compared to recycling costs, recycling technologies are underdeveloped, old devices are not collected systematically. A paradox. The nation that dominates rare earths is also the one least motivated to recycle them. Recycling, a solution for the future, but not a replacement for mining. Even if the world scales recycling aggressively, the rare earths already in used devices are far from enough to meet the soaring needs of EVs, robotics, wind energy, and electronics, sectors expected to double or triple in a single decade. Recycling can reduce dependence, reduce pollution, extend resource lifetimes, improve sustainability, but it cannot replace mining, at least not for the next several decades. So is recycling the real hope? The answer lies somewhere in the middle. Rare earth recycling is part of the solution, but not the entire solution. It is like a faint light at the end of a tunnel, enough to guide the way, but not enough to illuminate the whole path. Still, its very presence signals an important shift. The world has begun thinking about sustainable material futures, something that once focused only on speed and cost. And that shift leads us to a deeper layer. Humanity's psychological relationship with a group of elements that lack the glamour of gold or silver, yet evoke fear, belief, and obsession about the future. Sometimes there are strange moments in history, moments when what worries the world is not gold, oil, or food, resources everyone knows and recognizes, but tiny elements so small no one would notice them even if they were placed right in front of their eyes. Rare earths, with their plain chemical nature and utterly unglamorous names, have never been symbols of wealth. No one wears dysprosium around their neck. No one proposes marriage with a bar of neodymium. No one keeps europium as a family heirloom. They lack the natural beauty of gold, the ancient prestige of silver, the scent of power that oil carries. Yet somehow, rare earths have become the resource governments, militaries, and technology giants monitor more closely than diamonds. This is not just an economic story or a geopolitical one. Behind it lies a psychological story, one that drives human behavior more powerfully than any supply and demand curve. The first psychology, fear of the irreplaceable deep down. Humans fear losing control. We can replace steel with aluminum, replace copper with fiber optics, replace coal with solar. But when the modern world depends on neodymium magnets, electric motors, LEDs, radar, hard drives, sensors, robots, rare earths have no real plan B. Dysprosium lets magnets survive high temperatures. Without dysprosium, wind turbines stop. Without neodymium, EV motors weaken. Without terbium, screens dim and lose color. Without europium, the lighting industry falters. This irreplaceability creates a unique sense of unease, the sense that life can be disrupted by an element we have never even seen with our own eyes. This is why, when China cut exports in 2010, the world reacted much like it did when oil prices quadrupled, not because rare earths were expensive, but because they were impossible to do without. The second psychology, collective memory of disruption. Humanity has a strange memory. Major shocks, the oil crisis of 1973, the 2008 financial crash, the Cold War, the semiconductor shortages during COVID, all leave deep marks in the collective mind. When a global supply chain breaks, insecurity spreads faster than information. With rare earths, that fear is even stronger, because the shutdown of a single refinery can drag down the entire EV, wind energy, defense, and electronics industries. Industrial nations harbor a very primal fear. If rare earth supplies are locked away, the familiar world will stop. This is no exaggeration. Without NdFeB magnets, electric motors would become large and heavy again, robots would be slow, radar would be weak, aircraft would be less stable, and mobile technology would revert to the bulky era of the 1960s. This is not merely the fear of losing a metal. It is the fear of being pushed backward in time. The third psychology, rare earths as psychological insurance for the future. Across cultures, people always keep something in reserve in case of trouble. Cash in a safe, rice in storage, gold under the pillow, batteries, water, flashlights for storms. At the national level, rare earths have become a form of strategic insurance, not because they are precious like gold, but because they guarantee the continuity of society. A nation stockpiles neodymium not to get richer, but to ensure factories keep running during a crisis. A nation stockpiles dysprosium not to profit from higher prices, but to ensure EVs, radar, drones, and wind turbines do not grind to a halt. At the individual level, we seek peace of mind through small habits. At the national level, that peace of mind takes the form of rare earth reserves. The fourth psychology, the paradox of invisibility. The smaller and more invisible something is, the more we underestimate it, until it disappears. Rare earths have no smell, no striking color, no sound. They appear nowhere in ordinary life. They do not appear in movies or stationery. They did not appear in headlines before 2010. Yet their very invisibility makes them frightening, because we cannot clearly picture them in our minds. We only know they exist everywhere and cannot be absent. Humans always fear what they depend on but cannot see, and rare earths strike directly at that fear. The fifth psychology. Rare earths is a mirror of our anxieties about the future. Gold reflects fear of currency and stability. Oil reflects fear of economic disruption. Food reflects the fear of survival. Rare earths reflect fear of falling behind technologically. A nation without rare earths means no competitive electric vehicles, no stable clean energy, no strong high-tech industries, no modern radar, drones, or weapons, no material autonomy. And in the 21st century, falling one step behind can mean falling an entire generation behind. Rare earths become a symbol of the question, who will lead the future? And who will merely follow? When we look deeply into these psychological layers, we understand why elements once considered obscure have suddenly become the centerpiece of national strategy. Not because they are beautiful, rare, or mythical, but because they make people feel safe in a world changing too fast. But even though these fears are real, the journey of rare earths is not yet finished. Because after all the stories of technology, geopolitics, environment, and psychology, there remains one final chapter, where we look back across the entire history of these elements, from stardust to supermaterials, from forests to laboratories, from warfare to clean energy. A chapter that closes, but also opens, a larger question: what is the true legacy of rare earths? When we look back on the journey of rare earths from beginning to end, it is as if we are looking at a double map, one map of matter and one map of humanity itself. On the map of matter, rare earths begin as stardust, atoms born from the explosions of ancient stars. They drift for billions of years, settle into Earth's crust, lie still under rock, blending into minerals. They are discovered by Scandinavian miners as nothing more than a strange black stone. Then they enter the laboratories of Gadolin, Mosander, Welsbach. Men who could not have known their work would one day become the backbone of 21st century technology. From the rocks of Ytterby, the first glow of European gas lamps ignited. From there, rare earths entered World War II radar, nuclear reactors, the US-Soviet arms race, and satellites in orbit. Then, as the world shifted into the electronic age, rare earths became the heartbeat of motors, the core of wind turbines, the color of screens, the voice of speakers, the smoothness of hard drives, the precision of lasers, the intricacy of robotics, and the silence of electric cars. Seen through the map of matter, rare earths follow a straight trajectory, from the universe to the earth, from the earth to industry, from industry to technology, and from technology to the future. But the second map, the human map, is far more complex. On this map, rare earths carry opposing stories. They create the green of clean energy, yet leave behind deep green-black toxic ponds. They help electric vehicles run quietly, yet force mining villages to live beside the unending grind of crushers. They make screens brighter, yet dim the eyes of people living beside poisoned rivers. They are the foundation of future technology, yet the long shadow of past industrial decisions. We want a world with fewer emissions, less noise, and less dependence on oil. But to achieve that, we must face the truth that every green technology is built from materials of the earth, and no material leaves the ground without leaving a mark. Rare earths remind us that green is not colorless. It has the gray of mines, the reddish-brown of stripped earth, the deep blue-green of waste sludge, and the pale white of refineries hidden behind high walls. If we view this journey with purely practical eyes, we might say that rare earths are a paradox, enabling cleanliness while creating pollution. But history is rarely that simple. Rare earths also give humanity a lesson. Every advance has a cost. Every material has a shadow. Every technological system has a deeper layer we must acknowledge if we want to move forward. Yet within rare earths, we also see something few other resources show us: the capacity to learn, correct, rebuild, and innovate. The early efforts at recycling, small as they may be, are the first signs. Cleaner refining projects in Japan, the US, Europe, and Australia are the second sign. Nations like Vietnam and Canada, which are beginning to chart a path toward a cleaner industry, are the third. And the global pressure for environmental transparency and social responsibility is the greatest sign of all. Humanity will not accept an endless trade-off. Rare earths are not just a story that has happened. They are a story unfolding now, and one that will continue for decades. Now, as we close these 20 parts, we can step back and see the whole picture. From atoms drifting in space to magnets spinning in electric motors, from supernova explosions to conference rooms where the future of technology is decided, rare earths have journeyed from invisibility to the center of the modern world. They are the soft light on the surface, the glow of screens, of LEDs, of smart technology. But they are also the darkness beneath, the darkness of waste pits, of scarred forests, of communities wounded in silence. And between these two extremes, humanity stands on a crucial threshold. How do we step into the future without carrying our old mistakes with us? We do not know the answer. No one does. But rare earths leave us with a question worth contemplating. Can we build a cleaner, fairer, more sustainable world without forgetting to look at what lies beneath our feet? That question remains open, and humanity's journey to answer it has perhaps only just begun.